Okay, ladies and gentlemen, welcome to the first talk of this session. The speaker is Professor Pisier from Texas A&M University. He won the Frontiers of Science Award this year. He is going to talk about the tensor products of operator algebras today. Let's welcome.
Thank you very much. Thank you very much to the organizers. Thank you to the selection committee for this award. I'm absolutely delighted. As I've said in my thank you speech, but I had instructions to stop and not say too much. This paper was really very dear to me because what I do in the paper, as I will show you, is construct a C-star algebra that has a special property with respect to tensor products that has a property that when you tensor it with itself, the minimal and maximal tensor products coincide. And many years ago, I'm afraid that you see I was working already many years ago. In the 1980s, I worked on problems on Banach spaces that had been raised by Grothendieck. And one of my great joys of my youth as a mathematician was that I managed to find an example that answered a problem raised by Grothendieck. I produced the first Banach space that had the property that there was only one tensor product on the tensor product of the Banach space and itself. And for many, many years, I thought that I should be able to adapt the ideas to the C-star algebra setting. And I saw the work of Kirchberg that I will present and describe here. And for many years after I saw his work, I still wanted to do this. And this is what I'm presenting today in this paper. I finally managed. So it's the result of a long wish. Okay, so I will describe mainly two properties, lifting and extension for C-star algebras. And then I will come to the construction of the example in the end. But I thought I should probably give quickly some background. So very quickly, some background for those who are not too familiar with C-star algebras. So a C-star algebra is a closed self-adjoint subalgebra of the bounded operators on Hilbert space, and there are abstract ways to characterize it. Just the norm has this special property. And well, just some basic facts you need to know. The quotient C-star algebra is always a quotient by a closed self-adjoint two-sided ideal. So if I say ideal, it will always mean closed self-adjoint two-sided. And this is adapted to that fact here for any representation. So star homomorphism or representation is sometimes used, where the range is always isomorphic to the quotient of C by the kernel. So as you see, different from Banach spaces, here the range is always closed in particular, because this is the morphism on a C-star algebra. And incidentally, we'll work with, I'll try to limit that. There is a theory of operator spaces that's very active, but I try to minimize the use of it. So an operator space is just a subspace of a C-star algebra. So the C-star algebra sits in B of H, so the operator space inherits that. It's a space of operators. And whenever we have this situation, we have the space of matrices with entries in E that appears, so this Mn of E. Mn of E sits inside Mn of B of H, and so it can be equipped with the induced norm, the norm of operators on the direct sum of H n times. So all this is pretty obvious. So we have norm on Mn of E. And then when E is a so-called operator system, so operator system is a subspace which is also self-adjoint. It's still not an algebra, but self-adjoint and containing the unit inside the unit C-star algebra. And again, we can think of it inside, realized inside B of H. Then we have an induced order because we have a notion of positive. We have a positive cone on B of H, which we can induce. Okay, so all this to bring up the definition of completely bounded maps for those who are not too familiar with that. So a map U between operator spaces or between C-star algebras A and B, just linear map, is called completely bounded if this norm, the completely bounded norm, is finite. And this is the soup of the norms of the extensions of the map U to the matrix level by just this formula. So this is the obvious way to have U acting on matrices with entries in the domain. And if this map is uniformly bounded uniformly over N, then it's completely bounded. And we have, therefore, defined a completely bounded norm in this way. And this is the notation for the completely bounded maps from A to B. So that's a Banach space. Obviously, the ordinary norm is less than the CB norm because just looking at matrices of size 1 times 1, we have this. And a mapping, today I'll use mainly completely positive maps. Actually, a mapping is called completely positive if for any n, the mapping UN, which is here, is positive. That is positivity preserving. It takes positive elements to positive elements. And a very important remark with respect to these notions is that for maps that are unital, then actually completely positive is the same as what we call completely contractive, just having the completely bounded norm less or equal to 1. That's what we mean by completely contractive. If it's unital, of course, it means that the CB norm is just equal to 1. Okay, so now I have enough, background to, I hope, clearly define the lifting property and the local lifting property of C-star algebras, which are things that were introduced by well, not really, maybe formally introduced by Eberhard Kirchberg. More on that later. So the lifting property is like this. So the algebra A has the lifting property if for any, so let's say for unital C-star algebra, for any unital completely positive map, so UCP is unital completely positive, and you have here a quotient mapping. Okay, so you have an arbitrary quotient C-star algebra of an arbitrary C-star algebra C. You have the lifting property if any unital completely positive admits a lifting that's unital completely positive. So that's a pretty obvious notion. Now the local notion is a little bit more delicate. You, in the local notion, you don't ask that the whole map U lifts. What you're asking is that the restriction of U to an arbitrary finite dimensional operator system, so E here is finite dimensional. I hope it's not, I didn't forget it. So this is, we use the term, this is a localization. That's why it's called local lifting property. It's because we restrict to finite dimensional subspaces. So for any finite dimensional operator system here, I could say subspace actually for definition, but anyway, for any operator system, the restriction admits a lifting, which is again unital completely positive. So that's the local notion. And well, one of the problems that's nagging me that I've been working on actually quite a lot recently is it's a conjecture formulated by Kirchberg, which, well, I rather tend to think that it's wrong, but anyway, the question is whether the local property implies the global property. And this question is related to all sorts of similar questions, which actually are parallel in some sense, and it's very, very amusing, very striking. They're all open. So I can't resist not to mention at least one question which is open. Just take here a separable. That's important. You take a separable C-star algebra, and you take an ideal, and now you assume that U has norm 1, just norm 1. It is not known if there is a lifting of norm 1. So that's now in some sense, a Banach space question because you're forgetting the algebra structure and you're just asking, does norm 1 lift to norm 1? The amazing thing is that this was raised already in the 1970s, and this is still open. It's also something that I'm a bit obsessed with. Okay. So in various similar situations, like the one I mentioned, the problem is solved immediately if you have an assumption of approximation property. And I prefer to be vague, so I say, I say suitable approximation property. And it's fairly easy to sort of see heuristically at least the idea, right? We are restricting to finite dimensional subspaces. We're assuming we have something good on finite dimensional subspaces. So if this map U, or which is, somehow can be composed with the identity on A, so you could put the approximation assumption on U or on A. So, but let's say if the map U is approximable by finite rank maps, okay, then you're going to be able to exploit the local lifting and get to the global lifting. In fact, that requires work. What I'm saying now is not at all something obvious, but intuitively, it's sort of easy to believe, and I prefer to say it like that. So if you have an approximation property, usually you're okay. And in fact, this is the main example that was known of C-star algebra with lifting property was exactly of this kind. This was obtained by Choi and Efros, the famous result in 1977. It says that nuclear C-star algebras, and there will be more on that later, but nuclear, a C-star algebra is nuclear, say A, if for any other C-star algebra B, there is only one tensor product, one C-star norm on the algebraic tensor product of A and B. So basically, the algebra is nuclear if whenever you take another C-star algebra, you can build only one tensor product. And they proved that nuclearity, actually Kirchberg independently, is equivalent to the completely positive approximation property. That is that the identity is a pointwise limit of unital completely positive map of finite rank. So approximation is always by finite rank. And so then this idea that I was mentioning before works, and it tells you that you have the global lifting property. You have the global lifting property because before that, I missed a step. Before that, you have to check something, which is that the finite rank maps do lift. And actually, these finite rank maps that they obtain, they are factorizable through matrix algebras. And somehow the first step in that, the way that I'm describing, is that the matrix algebras are the first example. That's not surprising. They are finite dimensional, so approximability is obvious. But still, it's a non-trivial fact. The matrix algebras satisfy the lifting property. This is, you have to remember, this is by unital completely positive maps. And sometimes dealing with unital completely positive maps actually is more delicate than with morphisms. And then there is another major example with the lifting property, which was proved by Kirchberg in '94, which is the C-star algebra of an arbitrary free group, but it has to be separable. So a free group with, say, finitely many generators or countably infinitely many generators. That's an example with lifting property. And of course, these are very different kind of examples, because if you look at the C-star algebra of a group, so that's the C-star algebra generated by the universal representation of the group G, and it's nuclear if and only if G is amenable. And so you have, really two extremes, both satisfy the lifting property. It's sort of it's a strange fact. Now, in all this discussion, von Neumann algebras are excluded. B of H was known to be not nuclear already in '96, and we proved with Junge in '95, following Kirchberg's work, Kirchberg's questions, that it fails the local lifting property. An important fact which I should mention is that now that we know that this guy, C star F infinity, has the lifting property, somehow we can simplify the discussion, because this object, which will be very important in the sequel, in the second part of the talk, this object is fundamental in many ways. And in fact, that's because it is universal. Any C-star algebra, any separable unital C-star algebra, is a quotient of this guy. And so, in fact, you see immediately playing with arrows that the only map that really matters becomes what I write here abusively, the identity. That is, the isomorphism that identifies A with this quotient is the only thing you need to lift. Because if you lift this one, then, you know, since this guy up there has the lifting property, if you have any map from A to a quotient, you're going to be able to a UAP, a UCP map from A to a quotient. You're going to factor it through that space, because now this lifts through C, and so the identity of A is factorizable through this guy with unital completely positive maps. And so, so if you can do this, then you inherit the lifting property of this object, which needs to be proved, and which is not, you know, it's not at all obvious that it has the property. By the way, the proof of Kirchberg is quite involved, and one of the things I'm very proud of is that I found a very simple proof using a linearization trick that has been used for other things. But anyway, yeah, let's not say more. Okay. Now, another thing that I think is good to mention is that this object, which is universal for separable C-star algebras, has a companion which is almost the same guy, but which is a different algebra, which I denoted. I didn't know how to denote it in this way. This is the universal algebra of n contractions. And this is parallel to the C-star algebra of the free group, because C-star algebra of the free group is the universal C-star algebra of n unitaries. Okay? So I think it's pretty clear what is written. So the fact that this C-star algebra, C-star n, has a lifting property is very simple once you've checked this guy, because, you know, lifting by morphisms, now we are here lifting the identity so that the difference is not a UCP map anymore, it's a homomorphism. But it suffices to lift it by unital completely positive maps. That's the question. Okay, so for the free group, it's more involved, because it's not true that unitaries lift from quotient up to the algebra, which is under quotient somehow. The heuristic also behind that, parallel to the Banach space case, I can't resist also not to mention it, is that the span of the generators in both cases for these algebras is very naturally isomorphic to little L1 when n is infinity, or L1 n, the n-dimensional version in this case. And in the Banach space setting, it's very classical that these are the spaces that have lifting property. So I think it's kind of useful to insert here a brief discussion of a stronger property. So this is a stronger lifting property, which is called projectivity. So projectivity is the lifting property that you get by replacing completely positive everywhere by homomorphism. So it says if U is a homomorphism, then you can lift by a homomorphism. Okay. So that guy here has that property because of what I said, because, you know, all that matters is the generators, and your contractions here will lift into contractions, and then you map the star polynomials to star polynomials. You build the lifting star homomorphisms. And there are a lot of studies by Terry Loring and recently with Tatiana Schulman on this property, which I wanted to mention because they have a very recent result that I find quite interesting about an algebra which they call the soft tori. So this has a long, I should quote many, many references by also by Excel, Loring, and many others. So this algebra is a deformation between the C-star algebra of the free group. So here this is with two generators, and the C-star algebra of the abelian free group, because Z2 is the abelian free group with two generators, right? And so this is the universal algebra generated by two unitaries with the restriction that the norm of the commutator between U and V is less or equal than epsilon. So if epsilon is more than 2, of course, the triangle inequality tells you there's no restriction there. So this is just the free group and the C-star algebra of the free group that appears. And if epsilon is 0, then you're asking for U and V to commute. And so that's the free abelian. That's this algebra. And then in between, it's an interesting guy that varies in a mysterious way, perhaps from one to the other. And this brings me to a very unpleasant open problem here, which is that shows the limits of our knowledge. We don't know if the product of two free groups has the lifting property or the local lifting property. Yes. Did I make a mistake? Sorry? Yes. Epsilon is positive. Yes, epsilon is for me, yes, epsilon is positive. Thank you. Yes, epsilon is positive. But, yes. Okay. So, naturally, we say that the discrete group has the lifting property if the full C-star algebra of G has it. We see that amenable and free groups have the lifting property. And so it's not so easy to find counterexamples because usually, well, you don't get such a situation. And so perhaps not surprising to experts, of course, in group theory that I see, the counterexamples to the lifting property that have appeared are all related to Kazhdan's property T. So I remind you here that the discrete group has Kazhdan property T if the trivial representation is isolated in the set of all unitary representations of G. And there's a nice convenient definition that I like because it's in some sense is just an inequality. It says that the group, discrete group, has Kazhdan property if and only if there's a constant C such that the coefficients of any unitary representation satisfy this property. So the sup over the whole group of this difference is controlled by the sup over just a finite set of generators, a finite set, and then these will be automatically generated. So the classical examples are SLNZ for n superior or equal to 3. This has a famous history. I'm sure you've heard of it. And property T, of course, implies non-amenable for infinite groups. So here are the counterexamples. So the first counterexample was to the lifting property. I mean counterexamples to the lifting property. The first one was obtained by Ozawa. It was somehow not explicit. It was using a countable argument, using an uncountable family of groups with very special properties proved by Shansky and Gromov, rather complicated collection of groups. He said, he showed that there exists among this connection these groups, they all have property T, which fail the lifting property. Then Andreas Thom produced an explicit example, and recently Johanna Spas and Wiersma managed to really advance this question of producing counterexample by showing that the natural counterexample, groups with property T, SLNZ for n at least 3, all fail the local lifting property. But an interesting question here again, if you just have a group with property T, it's natural to conjecture it will fail the lifting property. This is not clear. What they showed here, which is also very nice, is that if G has property T and is infinitely presented, so it is not finitely presented, so it's a quotient finite group, finitely many generators, and infinitely many relations imposed on it, then the C-star algebra associated to it fails the lifting property. And there are uncountably many such groups, because in fact the original family of Ozawa, now we know they all fail the lifting property. Okay, so I come to tensor products, and I've already hinted that for me, everything starts with Grothendieck and Grothendieck's thesis in the 1950s. So he introduced there, of course, I'm not going to review that, he introduced there tensor products of Banach spaces, and in his theory appeared a maximal and a minimal reasonable tensor norm and corresponding tensor products. And actually very much at the same time appeared in Japan a theory for tensor products of C-star algebras, which I presume was influenced by Grothendieck. I'm sure the word had come one way or the other. And so Turomaru has very early papers, and then a lot of names, a lot of important contributions, Takezaki in France, Guichardet, and Lance, Choi, Efros, and Cohn's result plays a big role. Kirkberg and Wasserman, Efros Lance, Artvold Batty, Efros Hagerup, and the work that is really for me the starting point, the building block, is Kirkberg's work, Kirkberg's paper in Invenciones in 1993. So for C-star algebras, again, you have the same situation as in Banach spaces. You have a smallest tensor product and a largest tensor product. But here, this min reflects the norm being minimal, and the max reflects the norm being maximal. So what are these norms? So the minimal norm is easy to describe. If we go back to the realization of algebras inside B of H, so then the algebraic tensor product is realized inside the bounded operators on the I have a pointer, but I'm not using it. I prefer to use my hand. Bounded operators on the Hilbertian tensor product. That's the so-called spatial norm. And okay, there are background that I skip about that, but that's one way to write the minimal norm. And the maximal norm can just be written like this by this formula. You look at all possible star homomorphisms on the algebraic tensor product of A and B with the obvious product and star operations. And the soup overall these B of H norms gives you the max norm. And then you get the minimal and maximal tensor product after completing the algebraic tensor product with these norms. And here there is always a danger, which it's a little bit silly, but I like to emphasize that. A C-star algebra has a unique C-star norm. And this fact seems to contradict that. And when we say a C-star algebra has a unique C-star norm, we mean a C-star algebra which is a complete, which is a Banach space, okay? So this appears here. After completion, the norm is unique. But this is before completion on the algebraic tensor product. They are not, and when they are different, they're even automatically not equivalent because they would be equal. because of this uniqueness. Okay, so of course, if you have any C star norm, that is any norm that satisfies, this abstract axiom of C star algebras, which I mentioned in the beginning, which is just this one line, we call it, in France, we call it Gelfand's axiom, but anyway, that the norm of x star x is norm of x squared. That's what we mean by C star norm, a norm on the algebraic tensor product that satisfies that. Automatically, it's between the minimal and the maximal one. Okay, now more importantly, the maximal tensor product is projective, and this is quite parallel to Grothendieck's theory with Banach space tensor products. So it behaves well with respect to quotients. Yes, I call it projectivity, and also it behaves well with respect to embeddings, which I call injectivity. Okay, so anyway, that for morphisms, that indeed is just an injective morphism that corresponds to an inclusion. And perhaps it's important to explain why there are difficulties in this theory. Where are the difficulties? Very often the difficulties come from the fact that while this holds, so this is very nice for the max, very nice for the mix, for the min, well, the corresponding properties become wrong if you just inverse the roles of the min and the max. So the min is not projective and the max is not injective. And of course, this relation here complicates things when dealing with the max. One has to be careful because of that. Okay, so now formally, I like to work with just terminology a bit more general than what was used before. So I call a pair of C star algebras, I call nuclear, if there is only one C star norm on the algebraic tensor product, which means that the minimal and maximal tensor product of A and B are the same. They're identical. And of course, the classical definition of nuclear, which I recalled earlier, is that A is nuclear if and only if the pair AB is nuclear for all B. So for me, and for this is very much, the feeling you get when you read this paper of Kirchberg, there are two main C star algebras that you are concerned with. So the fundamental pair is the pair constitute of the full C star algebra of the free group. So that's the projective object because it has lifting property, and that's universal for quotient. And B, I call it like this quick B of L2, bounded operators on L2, which is also universal because any separable C star algebra embeds as a C star subalgebra in this one. Of course, this one is non-separable, but any separable embeds in this one. And here, any separable is a quotient of this one, which is separable. So that's quite a difference. Okay, so they are universal. And as we will see in a second, this object is also injective, while this one is projective because it has the lifting property. Okay, and these are fundamental for me. This is the fundamental pair. I note that early on it was proved, early for this algebra, a little less early for this one. This is in the 70s, Wasserman. These are not nuclear, okay? They are not nuclear C star algebras. Okay, so why B of H is injective? This is a whole lot of papers related to that. Basically, this is a result of Arveson that it has the extension property for unital completely positive maps. So if E and F are C star algebras or operator systems, any UCP map here has an extension which is UCP. So that's, call this the injectivity, we call this the injectivity of B of H. But we will be interested in a weaker form of injectivity, which goes back to a paper of Lance in 1973, which is called the weak expectation property. So I perhaps won't explain too much why it is called this way, but it's best to say that it is a weak form of injectivity. It corresponds to this. If you have a UCP map from E with values in B, well, you cannot extend it with values in B because that's injectivity, and I'm saying that this is more general. So the generalization is you can extend it by a unital completely positive map, but into the bidual. That is, you need to enlarge the range. From B, you pass to the bidual in order to have the extension. Now, Kirchberg's theorem say that there is a duality between these two properties, which is something a little bit surprising. There is a duality between the weak expectation property and the local lifting property. So the basic theorem is that it's a beauty, really, to me, I find this very beautiful. This pair of spaces, which is, I hope I've convinced you, super fundamental, because they're fundamental in two ways and parallel: injective and universal, projective and universal, etc. Okay, so the pair is nuclear, and more generally, Kirchberg proved that essentially, if you have, maybe let me start by, no, okay, let's say this here. So a C-star algebra has the local lifting property if and only if the pair formed of script B and C is nuclear. And this is actually the same as saying that you can pair this C-star algebra C with any WEP C-star algebra in place of script B, and you still get a nuclear pair. And here, exactly the parallel statement, reversing the roles. Now, a C-star algebra has WEP if and only if the pair which you get when you pair it with script C is nuclear, or the pair that you get with any LLP in place of script C is nuclear. So the thing to remember is that this guy is the prototype LLP, and this guy is the prototype WEP for the results that I'll be describing after that. And so the amusing way to summarize here this property is to say that the pair LLP-WEP is nuclear, right, in the sense that put any LLP, any WEP, you get this phenomenon here. And I think I got confused earlier. This is where I use a linearization trick to get a simpler proof. I might have said something, I might have got confused. Okay, so Kirchberg, in his paper, I encourage you to look at the paper because it's very fascinating at the end, the way he presents his conjectures. So he presents his conjectures in blocks. So there is a first block, the A block, and then there is the B block, and then there are other D, E, and so on. But the main thing is the A block and the B block, which are then, spelled out into equivalent forms, A1, A2, A3, and then B1, B2, B3, which are all equivalent. But essentially, he had the conjecture A that WEP implies LLP, and this we disproved fairly quickly with Junger in 1995. This turned out to be wrong. This was equivalent to asking whether the pair script B is nuclear, but it's not. And it's equivalent to saying that the algebra script B itself fails the local lifting property. Now, conjecture B, it's another story. Conjecture B was the converse. So, as you guess, he thought at the time that they were equivalent, but they're not. And failure of conjecture B now, in parallel, means that the algebra C fails the WEP, or equivalently that the pair script C is not a nuclear pair. But then he proved something that, really sort of startled everybody and raised a lot the interest on these tensor product questions, because this seemed to have very little to do with it being a C-star algebra question, very purely C-star algebraic. He showed that the conjecture B is equivalent to the cone embedding problem, which was, at the time, one of the main open problems on von Neumann algebras, von Neumann factors, and so on, whether essentially, a trace on a standard von Neumann algebra can always be suitably approximated by matricial traces, to say it very, very, very vaguely. And because I'm not going into that details. And this problem is equivalent by Kirchberg's work with just the question whether the pair CC is nuclear. So here the situation is difficult to describe, because there's a paper that appeared in 2020 by 5 authors that are here: G, Natarajan, Vidic, Wright, and Yuen. And their work contains a negative solution to the cone embedding problem. But they are specialists of, well, complexity theory, computer science. They use quite sophisticated arguments. The original paper is 200 pages long. And, well, it hasn't been verified by, say, someone in the community of operator algebras to sort of certify it. There's no reason to think that there's an error, because also it's been some time. But its situation is like this. So as far as I know, the paper is not accepted yet. But I could be just not informed. I'm not in the CS community. I think so. I don't think that they have a problem. But the problem is, of course, that they also are not willing to read the part that, yeah. Okay. So now let me get to what I did, to this example that got the award. So Lance, the original motivation is a question of Lance, fairly old question of Lance, who asked a very natural question. If you have a pair such that A and the opposite C-star algebra is a nuclear as a pair, does it force A to be nuclear? So this is, fairly natural, because I remind you, nuclear means that AB is nuclear for any B. So it's very natural to ask which B is critical. What B do you need to control the nuclearity of A? And the opposite, is the same C-star algebra with opposite product. Very natural, because it's well known that you have the standard form of the bidual von Neumann algebra of A involves a representation of A on the left and an anti-representation of A. So actually, it involves a pair of representations, commuting pair of representations on the pair AA up. So it really was natural to ask that. But Kirchberg produced the first counterexample, and his example fairly complicated, but I recommend the exposition in Brown-Ozawa's book for this example, although they don't do the complete proof, but the ideas are wonderfully explained there. So he couldn't get the LLP, and well, I could get it by this example here. So the point is that it gives a clearer solution to this question of Lance, because you see, what I do is I obtain a C-star algebra which has both WEP and LLP. And so if you remember what I said about the pairing between WEP and LLP, and if you observe that passing to the opposite, of course, is not going to change WEP or LLP because, you know, reversing the product doesn't change these structural properties of A. So this implies that the pair AA up is nuclear, and in some sense much more, but forget it, let's say we have at least that. And moreover, it's possible to construct this object, there'll be a little bit more on the construction in a second, in such a way that, well, two things. This C-star algebra script C embeds in completely isometrically in an ultra product of A, and in reverse, A embeds in an ultra product of the algebra script C, which means that locally, in the sense of finite dimensional subspaces, locally they have, you know, they are the same locally, they have the same local structure, which of course is important because if the cone embedding, let's for a moment, let's assume that the cone embedding problem has a positive solution. So you can recall that that means that the algebra script C is WEP. And this algebra is the model for LLP, or LP actually, but let's say LLP. So the algebra script C, if the cone embedding problem has a positive solution, the algebra script C itself is WEP and LLP. And so that's why it was so important for me to try to find an example that has the same property, both WEP and LLP, and that resembles the algebra script C, which is the object of the cone embedding problem. So actually, some of my friends, when I first presented this, reacted in a way which surprised me because I'm pretty much a negative guy. And they looked at this and said, oh, but this is positive, you know, because it goes in the positive direction, which is one interpretation, but it's not mine. Okay, so the example, the important thing is the example is constructed by local methods, so it's really finite dimensional methods. So this is not, it's an inductive limit. This is not at all, of course, surprising in C-star algebra theory, which is full of inductive limits. The point which is a little bit surprising is this is an inductive limit of subspaces, and most of the literature is about inductive limits of algebras, maybe algebras with approximate morphisms. Here, this is the case. The map in between is going to be approximately multiplicative with a rate of approximation that is summable. But the important thing is definitely En is not an algebra, En plus 1 is not an algebra, doesn't seem to become an algebra in the example. So it doesn't look like anything like the previous examples, as far as I could see. One super important ingredient, which for me was, it came last, so somehow that was really the eureka, was using the cone algebras. And using the cone algebra of this algebra script C turned out to be absolutely crucial. And this cone algebra is a major object for K theory, which I have never worked on. So that was a surprise. And the cone algebra is the unitization of this here, this tensor product, where you consider you could consider R plus, you consider the interval 0, 1, but open at 0. So some ingredients for the constructions are that this is actually what I'm describing here is a version which I've put on archive only a few days ago. It's definitely a simpler version, but it's based on a little more on the algebra C, because the original paper uses just the LLP. And I saw that if I used the lifting property, then somehow certain things become stronger, and it makes the construction easier. But what I liked about this new presentation, which as I said, I put on archive like a week ago, is that it starts with an embedding of the algebra C in L infinity C over C0 of C. So that's the usual limit, and in some sense limit algebra. The norm of an element here, typically represented by a sequence in C, the norm here is the lim sup of the norms. So that's this object is like a limit of sequence identical to C. So if you have an isometric homomorphism and you have a lifting which is completely contractive, so that expresses completely contractive, up in L infinity C, this is the basic ingredient we need to produce the inductive limits. So we have to extract a subsequence of the lifting, which is going to be, you know, a very lacunary sequence. And then we restrict it to a finite dimensional subspace, and we impose the thing which resembles, you know, an algebra is that we impose gradually this property here that the product of two elements in the ranges is at least inside the next linear subspace. Okay, so we get an inductive limit of this system, and we have two conditions. So I can describe in the original paper it was sort of more technical, but now I've sort of identified what I think are the two key assumptions. So one key assumption is this one. So this is just not any lifting in the sense that Fn needs to satisfy this property here, which is a little bit more technical. And then the other one, which is fairly natural, is that we impose on the homomorphism that we are lifting, the homomorphism capital F, we impose that it, in some sense, that it is WEP to in the end obtain WEP for the algebra. So for this is fairly simple. In the example that I have, I use a map that factors through, or it could factor through B of H, but if we want to stay with separable, it factors through some separable B with WEP. Okay, so there's another problem raised by Kirchberg in the same paper. I forget if it's labeled as D or something like that after A, B, or maybe it's problem C. I forgot to check. The problem is whether local lifting implies global lifting. And the motivation here is that he showed only one implication. He showed if the cone-embedding problem has a positive solution, then this is true. So if you like to formulate everything like me with tensor products, so if the pair CC is nuclear, this being the prototype lifting property, then it should be true that local implies global. So I conjecture that this algebra that I've constructed and that has, you know, that was constructed by local methods, it's fairly natural to think that it will fail the global lifting property. But it's been now quite a while, and I've tried to do it, so maybe I should be more prudent. Certainly, what I think is likely is that the example can be modified. That is, the tower of maps and subspaces that is the basic ingredient probably requires more work in order to insert in the inductive construction an obstruction to the limit having the lifting property. And so I'm working anyway in that direction. So all I can say is this last theorem here, which it's always very embarrassing. It's a theorem where I say the following assertions are equivalent, but I don't know if they're true or if they're false, but they're equivalent. There still is a slightly surprising element in there, which is that if this guy that I've just stated has the lifting property, then any C-star algebra separable with weak expectation property, for any such algebra, it will be true that the local lifting implies the global lifting. So just if you manage to show the lifting property for this algebra, so in other words, if my conjecture is wrong, I will have nice consequences, but you know, I still need to decide whether it's right or wrong, and this I can't do. So that equivalence between 1 and 2 is kind of amusing. And the third one, the equivalence with the third one is very frustrating because I could show that this is in fact equivalent to the fact that there is a completely isometric map from the algebra script C to itself, such that the min and max norm coincides on f of C tensor C, inside C tensor C. And of course, the cone equivalent, the cone embedding problem is just asking exactly the same as 3, but with a surjective map, because you know, if it's surjective, there are theorems that tell you that you know, that will be that will give you the result. It's perhaps, since I say completely isometric, it's maybe not immediate, but that's a known fact. Property of WEP that implies this. So I think I'm at the end. I thank you very much, and I end by an advertisement for my book. This book had a strange fate. I have to say, it's embarrassing. It came out. It's about the problem. It's about the Kohn. I call it the Kohn-Kirchberg problem. Now you know why. It's about tensor products of C-star algebra. It's a big book, too big, of course, like all big books. And it has everything about the equivalence of the Kohn problem with other versions, in particular the Zirelson. There's a version in quantum information theory due to Zirelson that plays a role in the solution you know, by Vidic and et al. But the book came out essentially at the same time, like the same month as the preprint with the solution came out on arXiv. So needless to say, it's not mentioned even. And even if I wanted to mention, it would be embarrassing because of other reasons, which is that, you know, since it was too early anyway to confirm things, it just could not be mentioned. So still, I think I can recommend the book. Thank you very much. Thank you.
Okay, any question?
Just didn't drink.
So there are many equivalent statements in your talk. So I just want to make sure I understand. So if your example fails this LP property, then Kahn's embedding problem has a negative solution. Am I right?
Yes.
Okay, thank you.
Yes, yes.
Any other question?
Yes, so you're absolutely right. I guess I was coming to the end and worried about time. So of course, yes, the whole thing was that if I can show an example like that failing the lifting property, it gives an alternate solution, a much more C-star algebraic solution to this Kohn embedding problem that definitely should be verifiable. Sorry.
Here we see many equivalent conditions to Kahn's embedding theorem, and now we know this theorem is false. So what do we learn as operator algebras from that result?
That it is false.
Yeah, just assume that's false, and then what do we learn from that?
Well, you know, difficult to too many things, too many ways to answer you. So I can't, you know, difficult to tell you in one sentence. So basically, if you're familiar with von Neumann algebras and you've read through the literature, you know, non-injective von Neumann algebras were not discovered immediately. So the connection with the free group, the factor of the free group giving, you know, non-injectivity, and this whole non-amino, it's the same parallel with groups. So what I think is that it's just opening the door to a completely, you know, new class of objects which are not approximable, by so it's like a new notion of non-amenability, which seems to be a huge how to say, a huge promise, because if you make it in parallel with what non-amenability created, then so it would have made the theory simpler. So it proves the theory is so you could say it proves the theory is complicated if you want to be negative, but you could also say it proves the theory is very rich, richer than it would have been if everything was closed.
There, as far as I know, people haven't translated the results in complexity theory back to operator algebra to construct explicit examples. I mean, so far as I know, the people in operator algebras haven't constructed examples inspired by those results in complexity theory, namely concrete examples that doesn't satisfy the constant embedding problem.
No, of course. Of course they have not.
So, but why not? Since that paper has been published online for 5 years. So
I thought I explained this, but maybe I was too. Yeah.
well,
Okay. No, maybe I was too shy because this is a little bit embarrassing discussion. And some people very serious people have looked at the proof, and they say from our area, and in particular Michael de la Salle, who did a Bourbaki seminar on it, and he says that he thinks it is correct, but he cannot certify that it is correct because it is using big boxes of results from complexity theory, or maybe, I don't think it's computer science, but say related to computer science, which are huge areas that represent whole theories, which for an outsider would take, like a year to absorb. And so he had to believe that these black boxes were correct, and then these one or two black boxes being correct, he thinks the proof is correct. So does that answer a little bit more your question? Why it was not possible to get inspiration from this solution to produce? Anyway, that's the fact. It hasn't been done, but many people are trying, have been trying.
Thank you.
Any other question?
So if I remember correctly, so in your solution to this golden ticks counterexample, for example, open problem of golden tick, the space is related to certain type.
Yes, it's related to cotype 2.
Then I would like to wonder whether there could be some non-commutative type in your.
There seems to be some analogy, but it's very, very vague. But anyway, I see it as some analogy, but it's that the property of, so cotype 2 is some sort of wild generalization of embedding in L1, and here I think the non-commutative case is embedding in this algebra script C, which for I'm always thinking in local terms. So for a finite dimensional space, to embed almost isometrically, almost completely isometrically in script C is the property that is analogous to cotype 2. But I couldn't do anything with this fantasy.
Okay, thank you.
Any question? Okay, if there's no question, let's thank Professor Pisier's beautiful talk again. Let's resume about 15 minutes.